Hi boys and girls, this is lecture 5.9, the topic numerical integration. This will be the last of the Unit 5 lectures. In addition to using rectangles to approximate area under a curve, an approximation can be found using trapezoids as well. In this first graph, we see upper rectangles being used to approximate area under a curve. This will be an over approximation of the area. Lower rectangles depicted here, an under approximation of the area. Trapezoids being used to approximate the area here. You can see that using trapezoids to approximate the area under a curve will give a more accurate approximation than an approximation using rectangles. Let's see how the trapezoidal rule is derived. The area of a trapezoid is 1/2 times the height of the trapezoid times the sum of the bases of the trapezoid. Let's use this formula to sum up the areas of these four trapezoids, which are approximating the area under this curve. Therefore, the combined area of those trapezoids will be 1/2 times the height of each trapezoid. This height can be found by subtracting the endpoints of the interval and dividing by the number of equal subintervals we choose. In this case, that's 4. So the height of each of these trapezoids will be b minus a over 4. Now let's factor out 1/2 in the height and then just add up the sums of the bases here. So for the first trapezoid, we have two bases, f of x sub 0 and f of x sub 1. Remember, these function values represent the height at x sub 0 and x sub 1. So the sum of the bases for the first trapezoid, f of x sub 0 plus f of x sub 1. For the second trapezoid, we have the function height at x sub 1 and the function height at x sub 2, which will be f of x sub 1 plus f of x sub 2. For the third trapezoid, we're going to have the function height at x sub 2 and the function height at x sub 3. That's going to be f of x sub 2 plus f of x sub 3. And then for the fourth trapezoid, we'll have the function height at x sub 3 and the function height at x sub 4, which will be f of x sub 3 plus f of x sub 4. Now, let's see what we've added here. Notice that the function height at the left endpoint of the interval and the right endpoint of the interval were added once, but all of the function heights in between were added twice, f of x sub 1, f of x sub 2, and f of x sub 3. This is because those function heights were serving as bases for two different trapezoids. The function height at x sub 1 was a base for the first trapezoid and for the second. The function height at x sub 2 served as a base for the second trapezoid and for the third. And f of x sub 3 was a base for the third trapezoid and the fourth. This result can be generalized in the trapezoidal rule. Let f be continuous on the interval AB. The trapezoidal rule for approximating the integral of f of x dx from a to b, which is the exact area under the curve f of x, is given by b minus a over 2n. This is the 1/2 times the height of each trapezoid b minus a over n times f of x sub 0 plus 2f of x sub 1 plus 2f of x sub 2 plus etc. 2f of x sub n minus 1 plus f of x sub n. Notice once again the function values at the endpoints of the interval are added once, but all of the function values in between are added twice. Moreover, as n approaches infinity, the right-hand side of this equation approaches the actual area under the curve f of x between a and b. All right, now it's time for an example. Let's use the trapezoidal rule to approximate the area under the curve sine x from 0 to pi. We'll use 4 subintervals and 8 subintervals and compare the results. So the integral from 0 to pi of sine x dx can be approximated in this way. 1/2 times the height of each trapezoid, which can be found by subtracting the endpoints of the interval, pi minus 0, and dividing by the number of subintervals we've chosen, in this case 4. So the height of each of these trapezoids is pi over 4. And now we'll need the function value at f of 0 once, or at 0 once, so f of 0 one time, plus 2 times the function value at pi over 4, plus 2 times the function value at pi over 2, plus 2 times the function value at 3 pi over 4, and then we'll need the function value at pi once. Now that means we'll have pi over 8 times 0 plus, and when I find these function values, I'll be multiplying them by 2. So this becomes square root of 2 plus 2 plus square root of 2 plus 0, which is approximately 1.896. Now let's use the trapezoidal rule with n equals 8. The integral from 0 to pi of sine x dx can be approximated by multiplying 1/2 times the height of each of these trapezoids, which will be pi over 8, and then we'll need the function value at 0 once, and then twice these function values, so that'll be 2 f of pi over 8 plus 2 f of pi over 4 plus 2 f of 3 pi over 8 plus 2 f of pi over 2 plus 2 f of 5 pi over 8 plus 2 f of 3 pi over 4 plus 2 f of 7 pi over 8 plus 1 f of pi. Now simplifying this gives me pi over 16, and eliminating the 0 function values and combining like terms gives me 2 plus 2 radical 2 plus 4 sine of pi over 8 plus 4 sine of 3 pi over 8, and that is approximately equal to 1.974. Now the actual area under the curve, sine x from 0 to pi, is 2. So you can see that as we increase the number of subintervals, our approximation got better. Another method for approximating area under a curve is Simpsons rule. Let f be continuous on the closed interval ab. Simpsons rule for approximating the integral of f of x dx from a to b, which is the area under the function curve f of x from a to b, is given by b minus a over 3n times the quantity f of x sub 0 plus 4 f of x sub 1 plus 2 f of x sub 2 plus 4 f of x sub 3, etc., plus 4 f of x sub n minus 1 plus f of x sub n. Notice the similarities between Simpsons rule and the trapezoidal rule. In Simpsons rule, we're multiplying by b minus a over 3n rather than b minus a over 2n. However, we are counting the function values at the endpoint of the intervals only once, just as we do with trapezoidal rule. But the subsequent function values are counted on an alternating factor of 4 and 2. The first function value after the endpoint of the interval is multiplied by 4. The next one is multiplied by 2. The next one is multiplied by 4, etc., until you reach the right endpoint of the interval. Of course, as n approaches infinity, the more subintervals you have, the closer the right-hand side of this equation approximates the actual value of the integral of f of x from a to b. Simpsons rule can also be derived using a weighted average of the midpoint and the trapezoidal rules. Here is a depiction of using rectangles with the midpoint in order to approximate area under a curve. And of course, here is the same curve being approximated by the areas of trapezoids. Simpsons rule can be found by taking 2/3 of the approximation using the midpoint rule and adding 1/3 of the approximation found by using the trapezoidal rule. In this last example, we're going to use Simpsons rule with 4 subintervals to approximate the integral of sine x dx from 0 to pi. Therefore, this integral from 0 to pi sine x dx is approximately equal to b minus a over 3n, which for this particular function is pi minus 0 over 3 times 4, which is the number of subintervals we've chosen, and that's pi over 12. So pi over 12. Then we're going to need the function value at 0 once, the function value at pi over 4 times, the function value at pi over 2 twice, the function value at 3 pi over 4 times, and the function value at pi once. Remember to alternate the factors 4, 2, 4, 2 for the function values between the endpoints of the interval. This is approximately equal to 2.005. That's the approximation of the integral of sine x from 0 to pi using Simpsons rule and 4 subintervals. Remember that the value of the actual integral is 2, so using Simpsons rule gives a very accurate approximation of that integral. That's it for today's lecture, and that concludes the Unit 5 lectures. I leave you with a great costume idea. You're welcome. God bless you, boys and girls.